Center of gravity for 2D. So for this video, and it's a continuation of the other one, what we're going to do is evolve this from adding together kind of discrete chunks of it into, we're going to replace the summation sign with an integral. And so instead of great big triangles and rectangles and things, we're going to split it into elements. But the idea behind these two is the same. It's still a moment. It's still kind of an R cross F sort of a deal to find the equivalent systems and to find that centroid location. We're just going to be defining smaller and smaller slivers for all of these little chunks that we're taking the moments of. And again, we can do this around the y-axis or the moment around the x-axis, and it's cross product, so y goes with x and x goes with y. We can do this for 2D shapes, or we can do it all along a line if you're dealing with a wire or a pipe or something. And we're going to replace the weights with areas for these systems. So if we have a uniform thickness, density times thickness, that density and thickness is on both sides of the equation, so we can get rid of it. And eventually, to get that centroid, it's the ratio, right? We're going to take that area over to the other side, and the area ratio is the same as a weight ratio if the density is uniform. And so whether it's R cross F or R cross A, it's going to be the same ratio, and the point of the whole thing is to get the position of the centroid. So we'll call that the first moment, and this is if we're going to be looking at it rotating around the y-axis, that's where we get the x centroid, and if we're rotating around the x-axis, we get the y centroid. Looking at a line, it's the same idea. So instead of R cross F or adding up the entire weight of the thing, that weight is created by using the density, the cross-sectional area, times the length. And since the density, and if we have something where the cross-sectional area of this is the same, we can get rid of density and cross-sectional area, and you can get the centroids based just on the length ratios rather than on the weights over here. So instead of R cross F, it's R cross a length instead. And again, we're just getting rid of the constant density and constant cross-sectional area for this guy. Okay, and I really do want to emphasize it is the same thing that we did before. So before we had an object, we split it into pieces, and the point of it is to find the location of the centroid, where all the pieces are. So we have all the pieces, we're finding an equivalent system of where those pieces add together, and the only difference for the calculus version of this is that when we divide it up into pieces, this is what our pieces are going to look like, okay, is a bunch of skinny rectangles, but each one of these will have to find the area of each piece, find the center of each piece, find the R cross F to each piece. So it's the exact same thing, whether it's little teeny pieces or big pieces. And this is all going to add up to one force acting at one location, and the location where that force feels like it's acting, that's the centroid. Okay, we're adding together each of these little rectangles, and we'll do that with an integral. But it's the same idea as we had before. So here we have our pieces, we're taking moments, we're looking at the center of each of these rectangles, and I'm going to try and convince everybody to not just plug through the calculus. I want you to actually draw in one of these elements that you're integrating over. Make sure you know where the center of the thing is, because the moment calculations, you have to know where the center of this is. That's going to go into those R cross Fs. The height of each of these guys, we're going to define that with some kind of an equation. So we'll have an object, and the shape of this object will be described by an equation, and that equation, we have to get the area of each of these pieces, right? The area or the force that's created by each of those, and the height of these comes from some random equation. So this is just an example of the type of equation that you could see in there. So let's look at one of these. So we're going to have to add up all of the areas, look at each of these individual pieces. So what's the area of this thing? Well, it's just a rectangle, right? What's the area of a rectangle? Area of a rectangle is base times height. You know this from second grade. Okay, if area of rectangle is base times height in calculus terms, what is this? What's the base of this? The base is dx, and the height is y, and we have some kind of an equation for y is. So all of these areas here turn into just y dx. It's just base times height. That's all it is. And if we want everything in terms of x, we're going to substitute the entire equation in here for what y is. So instead of y dx, we have some sort of an equation, and that equation has a bunch of x's in it, and this is how we can get the area. Okay, we don't just need the area though. This is a moment. It's r cross the area. So we need these position vectors as well. And the position vector is going to go from the axis of rotation to where the force is applied. And that is to the center of this element. I have to figure out where the center is. In terms of the x position, now these little elements are super skinny, so we don't have to say dx divided by 2 or anything weird like that. It's just going to be x. So the x position is the x position. Now the y scenario, these do have some kind of a height, okay? The height is how tall that line is. It's what the line is. And to find the center of the height, you just divide it by 2, okay? So we're going to take the equation for that line, divide it by 2, and that's the position vector for r cross f, or r cross a. So here's for our x centroid, and we have that lever arm multiplied by our area, and then for the y component of our centroid, we have that y lever arm. And this is the one that a lot of people forget, that it's not the entire y. This has a bar over it. We're going to the center of this little piece. So we have to divide our line in half because we're going to the center of each of these little rectangles, and then figure out what the area is. So this little guy, that's all of these little moments added together. So if we have x1a1 plus x2a2, all of these little chunks, all of these rectangles all added together, that's what this integral is. And all of these little pieces added together is going to be the total area of the entire shape altogether times that centroid of kind of where that force is going to act in the middle of it. So this is the big picture, the total area, and the centroid, and you get to the big picture by adding together all of these little individual elements over here in the integration sign. Okay, make your life easy on yourself. There's different ways that you can set up these integrals. There's more than one way to solve any problem. Let's just go through a couple of different possibilities here. So you can define your element vertical or horizontal. We can use polar coordinates, and depending on what shape you have, it's going to be a lot easier to go one way versus another way. And this is another reason, actually draw in the little element that you're going to be integrating over. Draw where the center of each of those little rectangles is to figure everything out. So let's say we have these vertical stripes. It's a rectangle. What's the area of a rectangle? It's base. Your base is dx. Your height is y. So there's your area. And then for x goes with x, y goes to y over 2. So that's the one we just did. What if instead of integrating from 0 to x and along the dx, what if we want to define our element in terms of dy instead of dx? And you can find the area either way. So in this case, it's just a rectangle again, okay? But what is the base of the rectangle? Well, let's say this distance is a minus x, so that's the length of the base, is a minus x. And then the height in this case is going to be, instead of dx, the height is going to be dy this time around. So our area is a minus x dy. And when we add all these together, we're going to get each of those out. So here's the center is up in the y direction, and then how about the x centroid? Well, it's halfway between where A is and where the line is. So kind of the average difference between A and the y. So here's where that x center position is. That's the lever arm for the x-axis, and here's our area over here. And sometimes an equation is easier to integrate with respect to y than respect to x, or just depending on the shape, one of these ways to set it up might be easier than another. Polar coordinates. So in this case, we're going to be integrating not dx, not dy, but d theta instead. So we're going to go around 360 degrees, or however many degrees you have. And the slivers we're taking are no longer rectangles. These are triangular slivers. And the height of the triangle is your radius, and the arc length is r times theta. So what's the area of a triangle? The area of a triangle is 1/2 base times height. So in this case, it'll be 1/2, and the length of this side is r, and the length of the other side is r theta. So here's our area, 1/2 r times r d theta. That's going to be the area of the triangle. And if you look up where the centroid is for a triangle in the Wikipedia table, it's 1/3 from the base or 2/3 from the very tip of the thing. So this is how far down that radius we're going to march in order to get to that central point. And you can break this up into x and y components so that you still have the area, the rotation around the x-axis and the y-axis. So x, that's the adjacent side to that angle, that's a cosine theta, so we're marching over here to get to the centroid. And then y, that would be the sine theta, that's the opposite side to that angle. So we're just finding the coordinate for the centroid of the triangle, and you're integrating with respect to the angle d theta. Let's walk through a sample problem. In this case, we have some two-dimensional object, and the shape of this object is described by an equation, and we have dimensions. Now, what the textbook likes to do is give you that equation in terms of generic terms, so they're not going to define what k is according to the dimensions. And I think they do that because a lot of these shapes you can actually look up in tables, but you're going to get the generic form of it, not specific to your particular application. So learning how to go between kind of the generic stuff that you'll find in the tables versus specific to you, that's a good thing to know. Okay, so determine by direct integration the location of the centroid of a parabolic spandrel. That's this guy right here. Before you start plugging in numbers, think about conceptually where it should be, so you can check your answer when you get it. And of course, it should be down here in this corner. It's almost like a triangle, right? So it's probably going to be close to what a triangle would be, which is 1/3 away from the corner. Okay, how are we going to solve this? Well, the first thing, we have to get a more specific equation. We have to, and sometimes you don't get an equation at all. You have to actually create an equation for your shape yourself. But you can, go into Excel and use some fitting parameters, and so you could create your own equation that describes the pile of sand or the pile of snow or whatever it is you happen to be looking at. So we'll come up with an equation to use, and then once we have that, that'll let us get the area of our object. And again, this is for 2D. So eventually area you can turn into weight, which turns into a force, but it's all proportional. So we're just going to worry about areas so far this time around. And then we'll decide what the least painful way to integrate this is going to be, right? So should we use vertical strips or horizontal strips? What type of elements should we be using for our integration? And find the moments, and the moments are what give us the centroid. Okay, so here we go. Let's figure out what a good equation to be. So we know this is some kind of x² parabolic spandrel type function. Just pick one point. We know the location of this top right-hand corner. okay? The XY coordinates, X is A, Y is B. Substitute that in for your X and Y components. So Y is B, X is A, and where those two are equal are only known, K has to be B over A squared. That's what would make this equation work for this particular case. So instead of kx squared, we now have a more specific form for our equation for the line. And like I said, maybe you don't start with an equation at all. You just have a shape and you throw some data points on there, and then you'll actually fit a curve and create your own equation for the thing. So here we have y equals b over a squared times x squared, and maybe there's some numbers you could throw in there. Some people like numbers better than letters. And another thing, maybe we want to integrate with respect to x or with respect to y. We can rearrange this so we have x in terms of y, or we have y in terms of x. So keep in mind that we can rearrange this guy to get whatever is going to make the calculus easier for us. Step number 2, evaluate the area. And this is where you're going to want to draw in your element, okay? So actually draw the element that you're going to use for this and decide how you're going to get the area. Okay, so remember our equation. The center times the total area is equal to each of those little pieces added together, right? So each little piece and the area of each little piece, or this turns into an integral of the centroid of each little element, and then the area of each little element. But eventually we need the overall area, so if we divide this by the overall area, that's going to give us our centroid, okay? So we need both the area of the thing and we need this moment calculation for the thing. Okay, so here we go. We've got our element. Let's just make a vertical one. They're rectangles. We know where the center of the rectangle is, and we're going to need the denominator over here and the numerator. So let's do the easy part first. Let's just find the area of the thing. So what's the area of a rectangle? Area of a rectangle is base times height. The base here is dx. The height is y. And y, we can substitute that in for that equation we found, right? So we're going to put the entire equation in here. And then we have everything in terms of x, and we're going to integrate from 0 to a. There you go. There's our area, 1/3 AB. Not too bad. So that's this piece of it. Next, we have to walk up and get the other piece, and that's going to give us our centroid. So here's the other piece of it. So we have our area. That's the same as we had before. So we have the height times dx. This whole thing is our area. But now we're going to add this little x in terms of it too. So this is like our moment. This is like r cross f. Only we're not using forces, we're using area. So r cross a. The position, not just to the element, to the center of the element. So remember, we're looking for the center of each of these little strips. In the x direction, it's the x coordinate. So all we have to do is multiply what we just had by x. So we have the area, we have x, so now we end up with an x cubed. So you get 1/4 x to the 4th, same thing, 0 to a. So it's similar to what we had before, right? So now we have 1/4 a squared b. That would be for the moment around the y-axis, and the moment around the y-axis gives us the x centroid. If we plug it in the other way around, so now we're looking at the moment around the x-axis in order to get the y coordinate. So, and this is, I hope you're good at moments because it really does come down to the moment. So for this one, we're looking at rotation around the x-axis, okay? And remember, when we take rotation around the x-axis, it's from the axis of rotation up to where each of those individual forces is applied. And we're going halfway through. So the center of the element, that's halfway up that line, okay? So we have our area. This is the area. And then this is that lever arm, the position to the lever arm. So you substitute in your equations, get everything in terms of x, and when you have each of these here, you end up with your x squared. For the integration on this stuff, this is not a math class. I don't want to turn this into a calculus class. So if you know some kind of math software like MATLAB or Mathematica, or maybe your calculator does it, feel free to use whatever math software you want to do the calculus on this thing. In fact, I encourage you to use some math software. From here on out, most people are going to use software, and it's really, once you know how to do calculus, you don't need to go through all that busy work anymore. Okay, so hopefully that makes sense how you set this up. So we have, this is all of the little bits added together. We also had the areas. So the final step is to find the centroid from this information. We could have also done this defining our elements differently, and we should get the exact same answer. Say that too. So here's the other way to solve for it. Okay, and hopefully that looks familiar to you. That looks like what we had in the other scenario as well. So if you want to check your answer, you can. Okay, so here's the last little bit. So this is, maybe write this how you're used to it. So we have the overall center, the entire area of the entire thing added together, and that is equal to all of those little bits kind of added together. Okay, so they're calling this Q, all of those little bits added together. So all we have to do to find x is to divide q by a. So there's the center in the x direction, there's the center in the y direction. And check this. Okay, so what's 3/4 a? Well, 3/4 over is something like this, and then where's 3/10 b? So that seems reasonable, right? It's over in the corner here somewhere is where our force is going to be applied. So make sure to check your answer to see that it seems reasonable. Just if you eyeballed it, it should be over there somewhere. And okay, I'll post some other examples too in the notes that you can study. Let me know if you want me to work through any more problems like this. Let me show you one more situation, and that's where you have two lines. So let's say you have some equation for this line up here. We can call this, I don't know, y2 and y1. So you have two different lines, two different equations, and the object you're interested in is created by the area between those two lines, and we want to figure out where the centroid of this thing is. Now, once again, there's two different ways to calculate the area, right? We could make our little strips vertical, or we could make some strips that were horizontal instead. And the question is, which way should we define this thing? Well, there's an easier way and a harder way to do this. So which way do you think would be the easier way? Give you a second to think about that here. What if we chose the horizontal method? Okay, so at the bottom, that is going to be bound by the two lines, but then we reach this point over here, and everything above that point, it's a different problem, right? So now we're not going between two lines anymore. We're going between some sort of a boundary condition. So we would have to break it up into kind of two different problems if we decided to define our elements sideways. Versus what if we decided to define our elements straight up and down? Well, it doesn't matter if we're at the top of it or at the bottom of it. Either way, those little rectangles, the area of those rectangles and the center of them, it's just going to be the difference between where the top line is and where the bottom line is. And that doesn't change for the whole problem. So this is going to be the better way to define our elements for this guy around. So you can see, and it's, you get all kinds of crazy different shapes. And before you jump into the calculus, just take a couple minutes to think through what would be the simplest way to attack these things. And a little bit of patience and foresight going into the problem will save you, hours of fighting with it later. So plan the best attack method before you jump into these things. Okay, try a couple out on your own.